Hello everyone and welcome to this episode of Linuxy tech hacky things, whatever it's called. Name will probably change eventually anyway. But today we're talking about hashing algorithms, how they relate to cryptography, and this will help us lead into tomorrow's topic, which is on Civic, the new app and blockchain-based service. I recommend anybody who doesn't have Civic app to go to the Play Store or iOS store and download it. If you are running Android without Google services, go to F-Droid, get Yelp, and download it. It does say that it needs Google Play services to run. However, I've used it just fine and no problems. Everything works. So I'm not sure what they need, but apparently it's not important. So yeah, let's get into this. So we'll start off with the hashing algorithm, just a basic overview of what hashing algorithms are. A hash function, which is what this function is, and the algorithm, and so on and so forth. But a hash function is any function that can be used to map data of an arbitrary size to data of a fixed size. So you can have a 15-page document, you can have a 100-page document, you can have a 1,000-page document, and you can encrypt it using some sort of hashing algorithm, or also known as a hashing function, and you'll always get a string of characters the same length. They're just different characters. Arbitrary size could be, like I said, 15, 30, 40 pages, like whatever, doesn't matter. It could be one letter, and you hash it, you're gonna get the same length as if you hash a 100-page document, so on and so forth. The fixed size is always so many bytes of information, represented in typically letters, uppercase, lowercase, numbers, and occasionally symbols, but I'm pretty sure it's not very common, at least from what I've seen. The values returned after you run this hash function are called hash values. They are sometimes called hash codes or hash sums. I just call them hashes. That's just what I call them. That's also a very common use. It's like, okay, when you take this and you encrypt it with a hash algorithm, you get the hash value. You get the hash. It's just called a hash. That's why I don't say hash values because I'm lazy. I don't want to say values all the time. One use is a data structure called a hash table. This is widely used in computer software for rapid data lookup. This isn't going to be what we're going to really talk about too much today. We're going to get more into the cryptographic side of things because of tomorrow's topic. But that is an option. With these hash functions, they accelerate table and database lookup by detecting duplicate records in this enormous file. An example is finding similar stretches in DNA sequences, and they're also very useful in cryptography, which we're going to get into in a little bit in coming segments here. A cryptographic hash function allows someone to easily verify that some input data maps to a given hash value. That's basically what it's for. It's saying like, hey, this information that they put in is this value, and it's easily checked against it. If the input data is unknown, it is deliberately difficult to reconstruct only given the stored hash value. So if I give you a hash value of whatever length it is, I say, here's my message. If you don't know how to decrypt that, it is as I wrote here, deliberately difficult. It's virtually impossible for you to figure out what the message is. This is used for assuring integrity of transmitted data. Often when you download a program online, they will come with a SHA-256 hash value that you can use to rehash it. So it's easy to hash, just difficult to reverse it. And if your hash matches their hash exactly, 100%, every character is exactly the same, capital, lowercase, numbers in all the right places, then you can be 100% sure that software that you have is from the company and it has not been tampered with. Because if a single bit of information is changed in the software, the entire hash is completely different. Every single character is different, and it's obvious. And I've used it several times when downloading versions of Linux and other software that is usually very important to have this kind of thing. In the coming segments here, we're going to talk about cryptographic hash functions, what is called degree of difficulty, applications for this, and also algorithms in general as it comes to cryptography. So let's get into that a little bit here, and Okay, so let's get into cryptographic hash functions and what this means. This is very similar to what we just talked about when it comes to just hashing algorithms in general, but it's more specifically used for cryptography. A cryptographic hash function is a mathematical algorithm that maps data of an arbitrary size to a bit of string of fixed length. The input is often called the message, and the output is often called the message digest or simply digest. This is identical to what we just talked about. All the same things apply. When it comes to cryptographic hash functions, there are four main properties that are typically considered needed to make a cryptographic level of hash function. 1. It needs to be quick to compute the hash value for any given message. So if I want to take a message and I want to encrypt it to send it to you, the listener, then it needs to do that quickly. I can't sit around for 20 minutes waiting for it to do the hash function. Also, it needs to be infeasible to generate a message from its hash value, except by trying all possible messages. This relates to the hard to reverse it. Basically, you don't want to be able to change it, because then that would essentially be a flaw in the system and your message isn't secure anymore. 3. A small change to a message should change the hash value so extremely that a new hash value appears uncorrelated with the old hash value. We just talked about this in the previous segment. This is more of a requirement for a cryptographic level hash function. And 4, it needs to be infeasible to find two different messages with the same hash value. If this does happen, this event is known as a collision, and when a collision happens, the cryptographic method of the hash function, whether it's MD5, SHA1, SHA2, is often considered broken at that point, and we move on to the next, a harder version. Cryptographic hash functions have many information security applications, notably in digital signatures, message authentication codes, and other forms of authentication. It's used in PGP and encrypting things between two users. Public key cryptography uses hash values, and Bitcoin and other cryptocurrencies, hence the crypto, use cryptographic hash functions to secure the information and do other things which we're not going to get into in this talk today. Information security context, cryptographic hash values. Can't read my own notes. Information security contexts include cryptographic hash values are sometimes called digital fingerprints, checksums, or hash values, even though all these terms stand for more general functions with rather different properties and purposes. So you may hear things being called as these hash functions, these outputs of digits and numbers, digits and letters of capital and lowercase values, as fingerprints, checksums, or hash values, but they're not technically the same thing as a cryptographic hash value. Even though they're used in that way, they're more general in what they do. Fingerprints can mean more than just cryptographic hashes. Checksums can be cryptographic, but they could just be regular hash with using the check if the content is the same. And just calling it a hash value is like, yeah, okay, cryptographic hash is a hash value, but hash values aren't always cryptographic. So that's very something. Wow. Today I can't talk. That is something that really needs to be thought about whenever you're reading these things, to make sure that it's not talking about something more general, and that whenever you are securely signing a message or encrypting a message for somebody, that it is using cryptographic hash functions. And that's easy to do. Just get PGP or go to keybase.io, and if you don't have an understanding of how to use PGP in a command line or on a computer program, they make it very easy for anyone to use. They have apps that you can use to chat securely, share messages, share content and stuff like that. They make it easy. So check out keybase.io for a very basic intro to PGP and cryptographic hash of messages to send to people and secure information. It's quite nice. So let's talk about degree of difficulty and what difficulty means to cryptography. So, in cryptographic practice, difficulty generally means an almost certainty beyond the reach of any adversary who must be prevented from breaking into the system for as long as the security of the system is deemed important. It's kind of confusing, but what it's saying is that difficulty relates to how hard it is to break the encryption, and the harder it is to break, the longer it takes to break. And you basically have the degree of difficulty relates to how hard you make it, and how hard you make it relates to how much security you need. So some government that needs very secure information for whatever, for national importance, they're going to want to use the hardest to break, the longest and hardest to break difficulty degree. Whereas someone who's just securing, like, I don't know, a text message that's not super important, but they don't want just anybody looking at it, you don't need as high of a degree. Doesn't mean you shouldn't use it, but you just don't need it. This meaning is dependent on the application, since the effort of an attacker may put into the task is usually proportional to his or her expected gain. This goes back to being the government or some bank or whatever. The bigger the reward, the harder they'll try. So your one text message isn't going to be a huge reward to them, chances are, and so they're not going to spend too much time trying to crack it. They might give you 5 minutes to crack it. If they can't crack it, they probably move on to somebody else. Don't take my word for that, but that's kind of how that works typically. Since the needed effort usually grows very quickly with the digest length, even a 1,000-fold advantage in processing power can usually be neutralized by adding a few dozen bits to the latter. So if you have a cryptographic hash, and say computing power doubles, and you're using SHA-256, you can easily take that message, decrypt it, and recrypt it in SHA-512, and you'll have the same level of security, even though the technology doubled that could break it, because you doubled the amount of bits that are put into it. This it's an inverse. It's like greatly increases as time goes on, and actually it'd probably be more than double, because it's like exponential increase. The more bits you put into it, the harder it is to break. The difficulty goes up drastically. Because cryptographic hash functions are typically designed to be computed quickly, special key derivations, I can't even say my own word I wrote here, functions that require greater computing resources have been developed to make such brute force attacks more difficult. So, we need this to happen fast. We don't want to encrypt something and wait around for 20 minutes to encrypt it. We want it to be encrypted so we can move on with our lives. So we have these special keys that give us derivatives of these functions. And these keys have passwords, which we talked about in the previous episode, that you need to have a strong passphrase for these keys specifically, because if someone gets your keys and they know your password, then they can encrypt and decrypt things that are made for you. But these keys give us the ability to make things much more difficult and save us time. So now we can encrypt things with 4,000 bits of encryption, and it won't take us 20 minutes to encrypt it or decrypt it. It'll take us, a couple seconds. Very important. This is a brush over, basically, of this. So if you know more than I do, please chime in. Such interpretations of difficulty are important in study of probably secure cryptographic hash functions, but do not usually have a strong connection to practical or security. For example, an exponential time algorithm can sometimes still be fast enough to make a feasible attack. Conversely, a polynomial time algorithm, example one that requires n to the 20th steps for n-digit keys, can be too slow for practical use. What this is saying is that there is always a trade-off between how fast we can encrypt and decrypt it, and how long it takes to encrypt and decrypt it, or how strong it is. So the stronger the hash function is, the better it is for security, but also the slower it's going to take to encrypt and decrypt it. So there's always a trade-off. How do we need this information quickly? So how strong can we make it and still be within a time frame that we need to use it? It's always something to think about, and everything has trade-offs. But as computers increase in their speed, the stronger they get, the faster our computers get, and so on and so forth. So let's review the applications for such a process here. So you're like, yeah, there's a lot of work, right? Yeah, it is, but luckily there's things that make this easier. So how do we apply this information, or how is it usually applied? So one way is that it's used to verify integrity of files or messages, which we kind of talked about. This is used to determine whether any changes have been made to the message or file, and this can be accomplished by comparing the message hash that was calculated before, after the person, when the person made it or the company made it, and after, once you received it. This is what we do when we download programs off the internet to make sure that they are exactly the program that I wanted and not someone's copy that they changed to make it malicious. In theory, if you can trust the company who made the original, you can trust that their hash is correct. Another way to use this is password verification, which is this is actually what LastPass does. So it's very important. If you don't have LastPass, guys, please get LastPass. Make a dice password for your master password. Don't use the same password twice anywhere. Like that is foolish. In this day and age, no one should be doing that. I just yelled at my wife about it because she still does that nonsense. But anyway, I yelled at her. I lovingly told her sternly. That's what we'll go with, yeah. But anyway, this allows the holder of the password, and like LastPass in this case, to store the hash digest of each password instead of the password itself. This is what they do for all your passwords, and also for your master password, so you can get into your password database. To authenticate a user, so that logging into LastPass, the password presented by the user is hashed and compared with the stored hash. The password is often concatenated with a random non-secret salt value before the hash function is applied. The salt is stored with the password hash, and because the users have different salts, it is not feasible to store tables of pre-computed hash values for common passwords. So what was all that? So basically what LastPass does is, I'm using them as the example because I know they do this. You have your password. You say, hey LastPass, I want to get in to my database. I want to see my passwords. You type in your password. They take your password. Your username has a salt, which is like just a string of characters. They call it a salt. Anyway, everyone does. They take that salt and they mix it in with they put that in with your, this is simplifying it, they take your password and your salt and they mix it all together and in this hash algorithm, and then it spits out this hash. And if that hash matches the hash on their servers that say your username and then your password, which is with the hash, if those hashes match, they let you in. The salt is needed so that you don't have instances where people are using the same password on the database showing the same hash algorithm. Because if everyone's using 1, 2, 3, 4, 5 as their password on LastPass, then every hash algorithm would be the same. And that's a big red flag. Well, red flag is it's a big key to hackers, like saying like, hey, let's work on this password. Let's work on this hash algorithm because this hash is the same as a lot of other hashes. So if we get this one, we get a lot of other people's as well. It helps with that because now you can't just crack one hash to get a bunch of different passwords. You just can only crack one at a time. Another application of hash algorithms are for proof of work, this is what Bitcoin's based off of actually. They use this proof of work concept so that they know that, hey, I found this Bitcoin in this block. I did the work, and then here's the proof, and it's all done cryptographically, which we're not going to get into how that works exactly because that is outside the scope of this talk. And another thing we have on here is file and data identifying, which is similar to verifying the integrity of the data, which we talked about previously. So a message digest can also serve as a means of reliably identifying a file. Several source code management systems like Git use a SHA sum of some type to uniquely identify the content within their systems and making sure that they don't mess up the systems. They're like, oh no, we have 2 different lines of code here and now they're all the same. So it helps keep things separate. And hashes are used to identify files on a peer-to-peer file sharing network like BitChute. If you're not on BitChute, it's awesome. Check it out. I hope BitChute is using cryptographic algorithms for their peer-to-peer sharing networks. So our next and final segment is going to be about algorithms, just in general, the history of it, where they came from, all kinds of stuff. So just a little bit of a recap. So thanks for listening, and we're going to get into this from right now. So finally, let's just talk about the algorithms that are out there in the world a little bit. So, there's a long list of cryptographic hash functions that exist. Many of them have been found to be vulnerable and should not be used today. There's a few examples here I have. In August 2004, there are weaknesses found in several of these. And as of 2009, the two most commonly used cryptographic hash functions at that time were MD5 and SHA-1. However, a successful attack on MD5 broke the transport layer security in 2008, and since has been deemed unusable. You can still use it. I mean, it's not like it's impossible to use. It's just not it's not considered safe because there's vulnerability has been found in it, and they can exploit that and get your information anyway. In February 2005, there was an attack on SHA-1, and it was reported that it would find a collision in about 269 hashing operations. So, rather than the expected 280 for the 160-bit hash function. In August of 2005, another attack on SHA-1 was reported that it would find collisions in 263 operations. Although theoretical, weaknesses of the SHA-1 exist, no collision or near collision has yet been found. When they wrote this, that is. That quote is from Wikipedia. Nonetheless, this is often suggested that it may be practical to break within years, and such that new applications can avoid these problems by using later members of the SHA family, such as SHA-2. SHA-2 is what is really commonly used. So if you download an application and they have a checksum, it's going to be an SHA-256, which is an SHA-2 algorithm. That's what's used commonly. They now have SHA-512 as well, which makes it even more secure, and that's better in the long run as things get more and more progressed towards complete and utter nonsense. Don't use MD5 to protect sensitive data. Don't use SHA-1 of any type to secure sensitive data. SHA-256 is probably what you would want to go with bare minimum if you're doing this kind of stuff. SHA-512 is going to be better. And if you're using PGP or GPG, I would say just default all of your stuff at 4096-bit encryption, because at the rate we're going, it won't take as long to crack a 2000 and whatever bit encryption. I forgot what the last numbers were. So keep this in mind, guys. Like, as things increase, things are going to get easier to crack. We did mention, I believe we mentioned in a previous episode that with quantum computers, we mentioned that even though things get better and faster, and so does our encryption, there are people that their whole lives are dedicated to making sure that there is some level of encryption that will not be breakable within a given time frame that is deemed acceptable. If you encrypt something with SHA-256, it takes a long time to break with your average computer. And that's good, because most people have average computers. Not everyone has access to, like, giant supercomputers, right? And just for some frame of reference here, the NSA, whether you love them or hate them, they do have a list of what they declare broken cryptographic hashes and acceptable. Currently, their only acceptable one, I think they have SHA-512. Well, I know that's on there. I think 256 is still considered to be okay, but they might have stopped using it. So keep that in mind. If you have like data at like NSA level security, you might want to use SHA-512. But yeah, guys, thanks for listening to this. This is a deep topic, and I mean, I'm still learning all this too. Like, this is by no means exhaustive and by no means thorough in my explanations here. It's grossly simplified, but I wanted to get that out of the way, more so to speak, so that tomorrow when we talk about Civic and its token, it has some background of cryptography. So thanks everybody so much. Follow me on Twitter, JRSwab. I'm on BitChute. I'm on YouTube. I'm on Gab.ai. I'm on Mastodon at JRSwab.
podcast you just heard was recorded with Anchor. If you want to make your own, download the Android or iOS app completely free from anchor.fm/podcast. That's anchor.fm/podcast.